Good afternoon. Today we will discuss the fundamental of network analysis. I am Dr. Avishek Das, Assistant Professor, Department of ECE, Haldia Institute of Technology. So first we will discuss what is the difference between network and circuit. Okay, so we go to the slide. First is my content. My content of the lecture. First is the concept of network and circuit. Second is the types of elements. Third, we discuss the types of source. Fourth, discuss the RLC used in network analysis. And next, we discuss the equivalent resistance, capacitance, and inductance. And lastly, we discuss some simple problem of network. Okay, so first is the concept of network and circuit. What is network and what is circuit? So first we discuss the network. What is network? Network is an interconnection of active and passive component such as resistor, inductor, capacitor, etc. They may or may not have a function. Okay, network can be open or closed loop. Whereas what is circuit? Circuit is a network having closed loop for flow of current and has a particular function. So you can understand if you go to the next slide. Here you can understand this one is the circuit and this one is the network. So circuit is a closed loop. Look here, resistor, inductor and the capacitor here all are connected and it is connected in a closed circuit or closed loop. So it is called the circuit. Whereas what is network? Network here are R1, R3, R2 all are connected and here one voltage source is there. But here one is the closed loop, another loop you can find it is open. So network may be closed, may be open. So we can understand that all circuits are network, but all network may not be a circuit. As because why? As because all circuits are network. Network may be closed or may be open. But to form a circuit, that is the network element should be connected in a closed path. Understand? So this is the difference between network and circuit. So we can say that is all the circuits are network, but all networks may not be a circuit. Okay, so next we go to the next slide. So in this slide we will discuss the elements of network and circuit. What are the elements? First is an active component. What are the first one? Elements are the active component. What is the active component? It is the electronic component which supplies energy to a circuit. Active elements have the ability to electrically control electron flow. All electronic circuit must contain at least one active component. So example of the active component are the voltage source, current source, BJT, FET, etc. That means the component which can generate the power in the circuit or network. This is the example of the active component which can generate or which can amplify the power. This is the example of active component. Next, what is the passive component? Passive component is an electronic component which can only receive energy, which can either dissipate, absorb or store it in an electric field or an magnetic field. So it cannot generate or it cannot amplify the power. This is the passive component. So what are the example of the passive component? Resistor, capacitor, inductor, all the example of the passive component. So this is the first one is the active component and the passive component, and this is the example of the active component and the passive component. Okay, in the next slide we will discuss the circuit element. Some elements are known as linear element and some elements, network elements, are known as the non-linear element. So what is the difference between the linear element and the non-linear element. So first we discuss the linear element. So what are the linear element? The linear element is also an electric element, and there will be a linear relationship between voltage and current. So for the linear element, example of the linear element are the resistor, inductor, capacitor, where the voltage and current has the linear relationship. If you increase the voltage, you can find the current is also increases linearly. So the element which has the linear relationship between the voltage and the current is known as the linear element. Whereas what is the non-linear element? The non-linear elements are electrical elements, and it will not have any linear relationship between current and voltage. For example, if you consider one diode, here this is the diode. So if we plot the voltage current relationship of the diode, we can know, that is, if we increase the voltage, we can know for the diode circuit, that is, the current flow is very small up to a particular voltage. Okay, that is called the cut-in voltage. After the cut-in voltage, current value increases exponentially. The current value is very high. So here for the diode, there is no linear relationship between the voltage and current. So diode is an example of non-linear element. Right? Next, we discuss the unilateral element and the bilateral element. This is also the network element. So what is the linear element and what is the bilateral element? One is the unilateral element, another is the bilateral element. So first we discuss the unilateral element. What are the unilateral element? The unilateral circuit element does not offer same resistance to the current of either direction. The resistance of the unilateral circuit element is different for forward current and that for the reserve current. Okay, so this is the unilateral element. Unilateral element means the in those element current cannot flow in both the direction. If we consider one diode, so it has the two side. One is the P side, another is the N side. So current can flow from the P side to N side easily, but reverse is not possible. From the N side, current cannot flow to the P side. Understand? That's because for the PN junction, diode can flow, current can flow from the P side to N side, but reverse is not possible. From the N side to the P side, current cannot flow. So diode is an example of the unilateral element. But what is the bilateral element? Bilateral element are the element, in those element current can flow in both the direction. So here the conduction of current in both direction in a circuit element with same magnitude is termed as bilateral circuit element. It offers some resistance to the current flow in both directions. So example is the resistance. So if you consider one resistance, current can flow from both the direction and we get the same amount of current. So resistance is an example of bilateral element, right? In the next slide, we discuss another type of element that is known as lumped element and distributed element. So what is the difference between lumped element and the distributed element? Lumped element are those elements which are very small in size and easily separable. Typically lumped elements are capacitor, resistor and the inductors. When we fabricate one circuit in your laboratory, in the breadboard, we connect the resistance, we connect the inductor, we connect the capacitor, and we can easily separate from the breadboard. So this resistance, inductor and the capacitor all are the example of the lumped element. As because here resistor, inductor, capacitor, we can easily separate those elements from the circuit. So this is example of the lumped element. Understand? So here resistor, capacitor, inductor are the example of the lumped element. Right? Next we discuss the distributed element. So what are the distributed elements? Distributed elements are those elements which are not electrically separable for analytical purpose. Distributed elements cannot easily separable. Understand? So what are the example of the distributed element? We can consider that is a transmission line. Transmission line, one simple example of the transmission line is your cable TV wire, coaxial cable. Coaxial cable, you know the coaxial cable. Here one inner conductor is there in the coaxial cable, right? So this is the example of the transmission line. But what are the equivalent circuit of the transmission line? You can find that is the one resistor. This is the figure for the equivalent circuit of the transmission line. Resistor, here the inductor, and the here G and the C is there, right? So this is the example of the, that is the distributed element. So this is the coaxial cable. This is the one transmission line. But what are the equivalent circuit of the transmission line? This is the equivalent circuit of the transmission line. And those elements, this inductor, this capacitor, this cannot be easily separable from the circuit. So therefore, this element is known as the distributed element. So this is the main difference between the lumped element and the distributed element. In the lumped element, that is the network element which can easily be separable from the circuit. This is known as the lumped element. Whereas the distributed element, the element which cannot easily be separable from the circuit. This is known as the distributed element, right? So next we go to the next slide. Next slide are the types of sources. We discuss the different type of sources. First one is the voltage source, right? So in the voltage source, we also, for the network analysis purpose, we use different type of source, right? First one is the voltage source. In the voltage source also, there are two types of voltage source. One is known as the independent voltage source, another is the dependent voltage source. So from the name you can understand, independent voltage source means which can generate the voltage independently. It does not require any help from any other component. That is why it is called the independent voltage source, right? So here it is written, a voltage source is a device that generate an exact output voltage which in theory does not change regardless of the load current, is known as the independent voltage source. So this is how it look like. This is the independent voltage source. We already know that is the battery source. One is the positive terminal is there, another is the negative terminal is there. We can also represent the independent voltage source with this symbol. This is also the independent voltage source. This is the symbol for the generator. Here that is the for the independent voltage source, that is the amount of voltage the independent voltage source generate. It does not depend on any other component of the circuit, right? And what is the dependent voltage source? Dependent voltage source is a voltage source those value depends on the voltage or current elsewhere in the network. So how we represent the dependent voltage source? We represent the dependent voltage source in this diamond shape. This is the dependent voltage source. You can understand from the name, dependent voltage source means it depends on the other circuit element or other circuit component. So what is the value of the voltage generated from the dependent voltage source? It generates the AVX, right? A is the constant and Vx is the value. And what is the Vx? Vx value we know from the circuit. So what is Vx? Vx is the voltage drop across the resistor. This resistor value is the amount is the R. Now if you change the value of the resistor in place of R, if you replace with the R1, then what happen? That is the voltage drop across this resistor. It is also changed. It will not be same as Vx, right? So if this value changes, that means that is the voltage generated from this dependent voltage source, that also varies. So you can understand that is the dependent voltage source means that is the what amount of voltage is generated, it depends on the other circuit component. Here in this example you can understand it depends on this resistance value. If you alter this resistance value, that is the voltage value generated in the dependent voltage source, that amount is also changes. That is why it is called the dependent voltage source, right? Next we go to the next slide. Next slide, similar of the dependent or independent voltage source, current source. In the current source also there are also two types of the current source. First one is known as the independent current source. What is the independent current source? Here, this is the example of the independent current source. We can represent the current source. This one is the generator. So a current source is an active circuit element. It is an active circuit element that is capable of supplying a constant current flow to a circuit regardless of the voltage developed across its terminal. So why it is called the independent current source? As because this current source can generate the current flow, and the amount of current is generated, it does not depends on any other circuit component or network component. That is why it is called the independent current source, right? Next, we discuss the dependent current source. Dependent current source means, from the name you can understand, dependent current source means it depends on the other circuit component or other network component. That is why it is called the dependent current source. So here it is written, dependent current source is a current source whose value depends on the voltage or current elsewhere in the network. So look how we represent the dependent current source. This one is the diamond shape. We can represent the dependent current source. This one is the dependent current source. And how much current it generates, this dependent current source, the value of the current is generated. The value is what? Value is the Cix, right? Cix. C is the constant and Ix is the what? Ix is the, here it is given in the network. Is is the current flow in the network. So what is the value of Ix? Ix value will be, here for the network, Ix value will be what? Ix value will be, if the voltage source value is the V and the resistance value is the R, so Ix value will be equal to V by R, right? Now if you change the resistance of this network, then this Ix value will changes, and if you changes the resistance value, that means that is the current generated by the dependent current source, that value is also altered, right? So that is why it is called the dependent current source. So for the dependent current source, the current generated or produced from the dependent current source is depends on the other circuit or other network component. That is why it is called as dependent current source, right? Next we discuss the next slide. So here we discuss RLC. R means resistor, inductor and the capacitor used in the network analysis. What are the resistor? Resistor is a passive two-terminal electrical component that implements electrical resistance. So how it look like? This is the symbol. This is the symbol of the resistor and how it look like, and what is the value of this resistance value. You can measure the resistance value using the color code. Different color code is there. From the color code you can calculate what is the resistance value of this resistor, or if you use the multimeter, using the multimeter also you can measure the resistance value of this resistor, and symbolically we represent the resistor with this symbol. So this is the resistor symbol. Next is the capacitor. Capacitor is a device that store electrical energy in an electric field. It is a passive electronic component with two terminals, right? The effect of capacitor is known as the capacitance. So the effect of resistor is known as the resistance and the effect of capacitor is known as the capacitance. How it look like? This is the one capacitor. That is, what is the value of the capacitance value? Here it is written, that is in the microfarad range. Okay, this is the microfarad range. So this is the value of the capacitance value of this capacitor. It has the two terminal. One is the positive. This one is the positive terminal. This one is the negative terminal. So this one is the polar capacitor. Is because it has the two terminal. One is the positive, another is the negative. Right. In the next slide, we discuss the inductor. So what is inductor? An inductor is also called as a coil. Right. It is a passive two-terminal electrical component that store energy in a magnetic field. Electrical, that is, inductor can store the energy in the form of magnetic field when electric current flows through it. An inductor typically consists of an insulated wire wound with the coil around a core. So this is the one inductor. So here it is the core, cylindrical core, and this one is the coil. It is wound in the inductor, it is a wound in a cylindrical core. The effect of inductor is known as the inductance, right? So in the network analysis, we only deals with the components of resistor, inductor and the capacitor and some sources. So sources are the voltage source and the current sources. So there are the two types for the network analysis. One is known as the network analysis, another is known as the network synthesis. Network analysis means what? Network analysis means one network will be given to you. You have to find out what is the voltage drop across the network, what is the current flow through any branch, that you can calculate or you can determine what is the value of the current flow through any branch or what is the voltage drop across any branch. That is known as the network analysis part, right? So one network will be given or provided to you. You have to find out what is the voltage drop across any branch or what is the current flow through any branch. You can calculate or determine the value. That is the part of network analysis. Another is the network synthesis. So network synthesis means that is the, if you want some amount of current, if you want some amount of voltage, it is given, that is the, you want to generate that amount of voltage or that amount of current, it is mentioned. So for that case, you have to design the circuit, you have to design the network. This is the part of network synthesis, right? So firstly, we discuss the network analysis. So for the network analysis part, in the network analysis, what component generally used? The component used are mainly resistor, capacitor, inductor and the voltage sources. Independent voltage source, dependent voltage source and the independent current source and the dependent current sources, right? So this is the part of the network analysis, right? So after the resistor, discussion of the resistor, inductor and the capacitor, we go to the next slide. Here we discuss the resistor is connected, what is the equivalent resistance value or what is the equivalent capacitance value or what is the equivalent inductance value if the resistor, inductor and the capacitor are connected in the series connection or in the parallel connection, right? So first we discuss the resistor when it is connected in the series connection. So first example is the series resistor. In a series circuit, the output current of the first resistor flow into the input of the second, right? So this one is the series connection. This one is the second example. This one is the series resistor. Here R1 and R2 are connected in the series connection. So what will be the equivalent value of the resistance value? R equivalent will be just simply R1 plus R2 is the equivalent circuit. If the voltage source value is the VB, so what is the value of I? I value will be equal to VB by R equivalent when the R1 and R2 are connected in the series connection. In the first example, R1 and R2 are connected in the parallel connection. So this one is the parallel resistor. So for the parallel resistor, what is the equivalent resistor? How you determine the equivalent resistor? Here the equivalent resistance value is equal to 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Here also, if you want to find out what is the value of the current value will be equal to VB by R equivalent. And here current flow in the R1 resistor and the R2 resistor, right? Here from the R1 resistor, what is the current value flow? It is the I1. And what is the current flow through the R2 resistor? It is the I2. So how you determine this I1 and I2? I1 value is equal to what? What is the value of I1? I1 you determine I1 is equal to what? Total current. Total current is equal to what? Total current is the I. This one. This one is the total current multiplication resistance of the other branch. What is the resistance of the other branch? R2. R2 is the resistance of the other branch. So here R2 divided by the total resistance. Total resistance is equal to what? R1 plus R2. So this one is the current flow in the R1 resistance. Similarly, what is the I2? I2 value is equal to total current means the I resistance of the other branch. What is the resistance of the other branch? Resistance of the other branch is the R1 divided by the total resistance. Total resistance is equal to R1 by R2. So we can find out the value of the current I1 and I2. This one is known as the current distribution rule. This one is the current distribution rule. For the parallel circuit, this total current I is divided. Here one part will go to this resistance value R1, another part current flow through this resistance R2, right? So total current I is equal to what? I is equal to summation of I1 and I2. But for the series resistor, total current, this I current flow through both the resistor R1 and R2, right? So here for the series resistor, the voltage drop across the resistor R1 and R2, those value are the different. So what is the value of V1? So to determine the V1, first you have to find out what is the current flow through this. So I is equal to, you can find out what is the current flow through this circuit. I is equal to what? You know the voltage drop. Voltage drop is equal to what? VB by total resistance. Total resistance is equal to R1 plus R2 is the total resistance flow through this circuit. We can determine I. Now what is the V1? V1 is equal to I into R1. V1 is equal to I into R1. Similarly, what is V2? V2 is equal to I into R2. You can find out you can determine what is the voltage drop across each resistor R1 and R2, right? So for the series resistor, what happened? The current flow through the circuit is same, but the voltage amount is different. So it is known as the voltage division rule. But for the parallel circuit, what happened? That is the current value is distributed or divided between the two resistance, but here the voltage drop across R1 and R2 is same, right? Next we discuss the capacitor. Capacitor, when it is connected in the series connection or when it is connected in the parallel connection. So this one is the series capacitor, this one is the parallel capacitor. Look, first example, capacitor is connected in the series connection. Here capacitance value of the first capacitor is the C1, second capacitor is the C2, similarly Cn minus 1 Cn. So up to n number of capacitor is connected in the series connection. So what is the equivalent or total capacitance value? Total capacitance value you can determine using this formula. Total capacitance is equal to 1 by C total is equal to what? 1 by C1 plus 1 by C2 up to 1 by Cn. You can find out the total capacitance value. Now if the capacitor is connected parallel connection, so here C1, C2 up to n number of capacitor is connected in the parallel connection, then what will be the total capacitor value? Total capacitance value will be equal to C total is equal to C1 plus C2 up to Cn. So you can determine what is the total capacitance value if the capacitor is connected parallelly and the capacitor is connected in series connection. You can find out the total equivalent capacitance value or total capacitance value, right? In the next slide here, so find the total capacitance for the 3 capacitor connected in series. Given the value, what is the value given? That is the 1, 5 and 8 microfarad. 1 microfarad, 5 microfarad and the 8 microfarad. So you have to find out the total capacitance connected in the series. So value of the capacitor C1, C2 and C3 value is given. So you have to find out the total capacitor or equivalent capacitor. So for that we apply this formula. For that you have find out the total capacitance value. If the capacitor is connected in the series connection, what is the total capacitance value? You can determine using this formula. 1 by C total is equal to 1 by C1 plus 1 by C2 up to 1 by Cn. So here the capacitor value, first capacitor value is the 1 microfarad, second capacitor value is the 5 microfarad, third capacitor value is the 8 microfarad. Just put into the formula, we can find out the total capacitance value is the 0.755 microfarad. The total series capacitance CS is less than the smallest individual capacitance value. So smallest when the capacitor is connected in the series connection, the total capacitance value is what? Total capacitance value is less than the smallest individual capacitance value. Total capacitance value is the 0.755, whose value is less than the smallest capacitance value, means the less than the 1 microfarad, right? In the next slide, we discuss the inductor. When the inductor are connected in the series connection or in the parallel connection. First, we discuss the inductor is connected in the series connection. This one is the series inductor. Okay, inductor are connected together in the series when they are used. Here the inductor L1, L2 and the L3 are the inductor, right? When they are connected in the series connection, what is the value? Total inductance value will be L1 plus L2 plus L3. So here is the one small example is given to you. You can understand easily. Here the 3 inductor value is given. What are the value? 10 millihenry, 40 millihenry and the 50 millihenry are connected together in a series combination with no mutual inductance. Mutual inductance, there is the no mutual inductance we consider between them. Calculate the total inductance of the series combination. Here the 3 inductance value is given. What are the value? 10 millihenry, 40 millihenry and the 50 millihenry. So you have to find out what is the total inductance value. Total inductance value will be equal to the summation of the all the inductance value L1 plus L2 plus L3, and you get the value is the 100 millihenry, right? Next we discuss the parallel inductor. So parallel inductor means the here if the inductor L1, L2 and the L3 are connected parallelly, then what will be the equivalent inductance value or what will be the total inductance value? Total inductance value will be equal to what? Total inductance value will be 1 by LT. 1 by LT is equal to what? 1 by L1 plus 1 by L2 plus 1 by L3. If there are n number of inductor is connected parallelly, then we can determine the total inductance value. It is up to 1 by Ln. So we can determine what is the total inductance value, right? So up to this we can find out, that is the when the resistor, capacitor and the inductor, if it is connected in the series connection or it is connected in the parallel connection, we can determine what is the equivalent resistance value, what is the equivalent capacitance value, what is the equivalent inductance value if the resistor, capacitor and the inductor is connected in the series and in the parallel combination, right? So if the value is given of the inductance value or the capacitance value is given, and if it is connected in the series connection or in the parallel connection, you can easily determine the total capacitance or total inductance value, right? In the next slide we discuss, that is we discuss some problem. Here one problem is given. Look, find the equivalent resistance value is given. So up to this you know, that is the when the resistor is connected in the series connection or when the resistor is the connected in the parallel connection, you can find out easily what is the equivalent resistance value or what is the parallel when it is connected the parallelly, you can easily determine what is the equivalent resistance value. So in this example or in this problem, here some resistor is connected, right? We can find out what is the equivalent resistor value. Here the resistance value R1, R2, R3, R4 and R5, and the value is also given. So R1 value is the 2 ohm, R2 value is also 2 ohm, R3 value is the 1 ohm, right? R4 is the 2 ohm, R5 is the 5 ohm. Here it is given, and this terminal X and Y, you have to find out what is the equivalent resistance. So to find out the equivalent resistance of the problem, first of all you have to see carefully the network, and you have to understand what resistance is connected with the other resistance in the series connection or in the parallel connection. You have to carefully check the network. Then you can easily understand what resistance are connected with the other resistance in the series combination, or what resistance is connected with the other resistance in the parallel combination. If you can understand what resistance is connected to the series combination and the parallel combination, then you can easily find out, or you can determine the equivalent resistance value. And if you can equivalent resistance value, you can step by step you can find out the total equivalent resistance value. So for this problem, how you solve what is the equivalent resistance value, in the next slide we discuss how you determine the equivalent resistance value. Look here, for the find the total equivalent resistance value, what is the solution? Look here, R1 and R2, this resistance value R1 and here R2 are connected parallelly, right? Look carefully, this terminal and this terminal. So here R1 and R2 are connected parallelly. So what is the equivalent resistance of these two resistors? R equivalent is equal to 1 by R1 plus 1 by R2. So R equivalent value will be equal to 1 ohm, right? So here in place of R1 and R2 we write its equivalent resistance value. Equivalent resistance value is the 1 ohm, right? Next, what is the equivalent resistance for here? 1 ohm resistor and the this 1 ohm resistor and the R3, these are connected in the series connection. These two resistance is connected in the series connection. So what will be its equivalent resistance? Here it is also 1 ohm, it is also 1 ohm. Total equivalent resistance will be equal to 2 ohm, right? So next here, look, this R4 resistor and this resistor are connected parallelly. This 2 ohm resistance and this 2 ohm resistance are connected parallel combination. So parallel combination, what will be the equivalent resistance of the 2 ohm resistance when connected in parallelly? Its equivalent resistance will be 1 ohm. This is the 1 ohm, right? So what is the equivalent resistance here? Lastly, there is the one resistance R5, value is what? Value is the 5 ohm, and the equivalent resistance we determined up to this, it is 1 ohm. So total equivalent resistance is equal to what? Total equivalent resistance is the 6 ohm across the terminal XY. Across the terminal XY, what is the equivalent resistance value? Total equivalent resistance value is the 6 ohm, right? So this is the another problem. You try yourself. Find the voltage drop across the 1 ohm resistor. This one is the second problem. Here look, this is the 4 ohm resistor. This is the 4 ohm resistor is connected. After this one is the 2 ohm resistor. This is the 5 ohm resistor, 5 ohm resistor. Here you have to find out the voltage drop across the 1 ohm resistance and power loss across the 2 ohm resistor. Where is the 1 ohm resistor? Here. The R3 value is the 1 ohm resistor. So you have to find out the voltage drop. You have to find out the voltage drop across the 1 ohm resistor, and you have to find out power loss across 2 ohm resistor. Where is the 2 ohm resistor? Look in the network. Where is the 2 ohm resistor? This one is the 2 ohm resistor. This one is the 2 ohm resistor. So how you determine what is the voltage drop across the 1 ohm resistor? So for that you have to find out. So for this circuit here, look, the value of the current value is the 10 volt. 10 volt. It is not given in the problem. Here it is given the 10 volt voltage source. So if it is the 10 volt voltage source is given, you have to find out what is the current flow through this branch. You have to find out what is the current flow through this branch. If you know the current flow through this branch, if this one is the I1, you can find out the I1 value. Then you can find out what is the voltage drop across the 1 ohm resistor. Voltage drop value will be equal to V is equal to I into R. So if you find out the I1 value, you can determine the voltage drop across this 1 ohm resistor. Similarly, you have to find out what is the current flow through this branch. Suppose the current flow through this branch is the I2. If you know the current flow through this branch, you can determine the power loss. P is equal to what? P is equal to I square. P is equal to I square into R. So if you find out the I value, I value means here it will be the value will be I2. So if you can find out the I2 value, so you can find out what is the power loss across the 2 ohm resistor, right? So try to solve this network. You already know how to determine the equivalent resistance for the series connection, for the parallel connection, you already know. So easily you can find out, or you can determine what is the equivalent resistance, and you already know the current distribution rule for the series connection and the parallel connection we already discussed. So from that you can determine I1 and I2, and if you can find out the value of I1 and I2, you can easily determine what is the voltage drop across 1 ohm resistor and what is the power loss across the 2 ohm resistor. Do it yourself. Okay, thank you. We meet to the next slide.